Let us discuss about the packing efficiency. So this concept is very important because from this chapter, so here the main derivation parts will be coming here from this packing efficiency. That is called find out the packing efficiency, simple cubic unit cell, find the packing efficiency, body centered cubic unit cell and face centered cubic unit cell. So let us see the definition of this packing efficiency. The packing efficiency which may be defined as the percentage of the total space which is going to be filled by the particles. Total space, how much it is going to be covered by this particle, we are going to find out here. So that is using this formula, that is packing efficiency, that is equal to the volume which is going to be occupied by a particle in a unit cell into 100 divided by the volume of the unit cell. So by now this formula we are going to calculate the packing efficiency in all the three parameters. And this is also very important here because the spheres which you are going to draw here, so that is that volume of one sphere that is equal to 4 by 3 pi r cube. So this is also important, here it comes in the derivation. So if you know these formulas, that is packing efficiency and volume of one sphere, we are going to find out the packing efficiency derivations in all the three parameters. Let's start the derivation of the simple cubic unit cell, that is called packing efficiency. We are going to find out the packing efficiency in the simple cubic unit cell. So this is the derivation is very important and it is very easy to understand, right? So this is a cube, right? So this is a cubic unit cell. So these are the two spheres which are going to be contact with each other. These two spheres, hot spheres, which are going to be contact with each other, and you know this. So these are called as constituent particles. So here totally 8 particles will be there. So these are going to called as the corner particles also. So these two we are going to call as the corner particles, and here 8 total corner particles will be there, right? So then 2 spheres will be there. And you know that cube, here I am going to take these are the sides of the cube, right? So these will be called sides. These are the sides of the cube. That is called A. I am going to make it as A. So this is also side. This is also side. This is also and side, right? And this is also and side. A. So let A be the side of the cube, or what you can tell, there is a edge length of the cube I can tell. Let A be the edge length of cube, right? So these are A are sides of the cube also you can tell. And you know that next I am going to take the terms as let R be the radius of the cube. Radius of the cube. Why? How it came here radius? Because of the spheres. One sphere means which will be containing the radius, right? So I am going to take. So this is from this nucleus to this side, that is 1r, and from this nucleus to this side, that is called r. So in a edge length, that is in one side, there will be 2r will be there, right? So here this is 1r and this is 1r. So this is the relationship between the edge length, I mean side of the cube, and radius of the cube. So that relationship I am going to write as A is equal to how many r? So in a side 2r will be there. This is the one radius. This is one radius. That is called A is equal to 2r. This is a simple one. And you know that in simple cubic unit cell, how many particles will be there? Let's say we have derived already, right? So in simple cubic unit cell, only one particle will be there. How? So you know how to find out that one. So in the total corner particle, 8 corner particles will be there, right? These 8 constant particles, in each particle which is going to be shared by some other 1 by 8 particles, right? That is called 8 into 1 by 8. We got in simple cubic unit cell, there will be only one particle will be there. So because this is a simple cubic unit. Therefore, in simple cubic unit cell, only one particle will be there. Only one particle. So now I am going to write the formula for this one. So you know that this one, that is called packing efficiency, or simply you can write here PE, right? So packing efficiency, that is equal to volume of one sphere. That is equal to volume of one sphere. Why I am going to take only one sphere? Why not these two spheres? Because simple cubic unit cell, how many particles will be there? Only one particle will be there. So that's why I am going to take consider the only one sphere. That is called volume of one sphere into 100 divided by volume of the cube. divided by volume of the cubic unit cell. And you know that volume of cube is equal to, so you know that in a cube that will be length into breadth into height. So this is the formula for the volume of the cube, length into breadth into height. So what is the length here? So this is the length, everything will be same. Length will be a, breadth will be the a, and height will be, this is height. So this is also an a. So how many? So that is called 3 times of a, that is called a cube. That is called volume of the cube is equal to a cube. And what is the a, you know? So that is called a cube. I am going to write as the, so I am going to cubing this one. So 2 cube, 8. And this r, it becomes r cube. So like this, we got the volume of the cube. So directly we are going to substitute in a formula. That is called packing efficiency in a simple cubic unit cell, that is equal to volume of one sphere. You know that volume of sphere, that is called, I told already, it is a 4 by 3 pi r cube. 4 by 3 pi r cube into how many particles? Into 1 particle. That is understood. If you, so only you can write 4 by 3 pi r cube or into 1. That is not a matter. That is called 4 by 3 pi r cube only. Into 100 will be there and divided by volume of the cube. Volume of the cube, how much you got? That is called 8 r cube. So now it is a simple calculation. This r cube and this r cube going to be cancelled here, and this 3 which is in the denominator, which comes in the denominator, what happens? That is called 3 into 8, that is becomes the 24. That I am going to write 4 by 24 and remaining pi is there into 100. Simple calculation. So this is a 4 1 4 6, right? So this is called now pi by 6 into 100. Pi, you know the value, that is called 22 by 7. After the simple calculation, you are going to get the pi value as the 3.14. 3.14 into 100 divided by 6. You are going to obtain the value as 52.4, and 100% will be there because we are going to find out in percentage, right? That is called 52.4 percentage. Packing efficiency will be there in simple cubic unit cell. So this is the simple derivation to find out the packing efficiency in the simple cubic unit cell. So you know that, so you got the packing efficiency, right? So we are going to find out the vacant space. So how we are going to find out the vacant space? Therefore we are vacant space available in simple cubic unit cell, that is equal to 100, total 100 minus 52.40 percentage. That is remaining, we are going to got the vacant space. 47.6% will be the vacant space. This is the vacant space, right? So this is the packing efficiency in the simple cubic unit cell. So let's derive the second derivation, that is called packing efficiency in face-centered cubic unit cell, or it is also going to be called as CCP or HCP. So this is called face-centered cubic unit cell. So here once again, so these are the 3 spheres which are going to be contact with each other, and these are the 8 constant particles, and these I am going to consider as these 2 are the corner particles. So in these corner particles, 3 spheres which are going to be contact with each other. So let's start the derivation. It's very simple. So and you know that, so this is a cube means, so and now I am, you know this as the name indicates, a face. Each face of the side, so you have derived it, right? So face-centered cubic unit cell, there will be total 4 particles will be there. We are going to consider this face, total 6 faces will be there. Face-centered cubic cell, so face means like this. So this face, face like this. So right, so I am going to consider for the calculation method, I am going to consider only this face, and now I am going to join these lines. So how many R will be there? So like this, these are called the radius. So I am going to join these one. So 3 spheres touching with each other, and this sphere is having the radius, that is R, right? So here 1 R, 2 R, 3 R, 4 R. You are not going to consider this one, right? This is on this radius and this is half of this radius. Total B is equal to 4 R. So let A be the side of the cube or also adjacent length of the cube and or with the radius of the sphere. So here B is equal to, I am going to write B is equal to directly, B is nothing but this distance, and this distance I am going to call as the B. This is called diagonal. This is called diagonal, and remaining these are called the sides. These are called the sides of the cube, and this I am going to call as the B. So B, this is called diagonal. So diagonal from this point H to this point C. Therefore B I am going to write as HC. Right? So this is called diagonal. I am going to consider only one face for the simple calculation method. HC is equal to B, B is equal to 4R. This one radius, this is the 2 radius. Spare this 2 radius will be there, and this will be the 1 radius. So total B is equal to 4R. So this I am going to call as the equation number 1. 4R will be there. And by looking this one, so this you are going to find out in this triangle, right? So please observe this one. So this I am going to call as the triangle. So this is an one triangle will be there. That is called in triangle DHC. In triangle DHC. So this is a triangle DHC, and this is called diagonal. So when the diagonal comes, so we should remember the Pythagoras theorem. So what it does, Pythagoras theorem? So Pythagoras theorem, this is a diagonal. So this is the length of the side, which will be more. So that's why in triangle DHC, so this is called HC square is equal to sum of the squares of the remaining sides. What are the remaining sides? So this is HD and this is CD. That is called HD square plus CD square. HC square is equal to HD square plus CD square. HC is nothing but this one, this diagonal. What is this name? B. That is called B square is equal to HD square. HD distance is nothing but the right A, and CD is nothing but the A. So that is called A square plus A square. So when you join this one, B is equal to square root of the A. Right, because B square is equal to A square plus A square, 2A square, and in order to remove this square, so that 2A square becomes, this is the root, and A square becomes the, when you are going to take the, under the square root, 2 and square root cancel, you are going to obtain the root 2A. So this is equation I am going to calculate as the 2. So and here, so see here, B is equal to 4R and B is equal to root A. So we are going to equating equation 1 and 2. Equating equation 1 and 2. What happens? Equation 1, that is called 4R is equal to root 2A. I mean, I am going to find out the relationship between the radius and the side of the cube. That is called adjacent of the cube. So what is that? A I am going to take here. Therefore, A is equal to 4R by root 2. 4R by root 2. How I can rearrange this one? A is equal to, this denominator is root 2 as it is will be there. 4 I am going to write as 2 into 2R, right? 2 into 2R. And remaining 1 2 I am going to write as root 2 into root 2. Because root 2 into root 2 is nothing but the root 4. Root 4 is nothing but the 2. Therefore 2 into 2R becomes 4R, right? This one root, because of the simple calculation, I am going to write like this. This root 2 and this one root 2 will be cancelled. What is the remaining? Therefore, A is equal to 2 into root 2 R. So this is the, I am going to find out the value of the A. This is from these equations, from these Pythagoras theorem, applying this Pythagoras theorem, we are going to obtain the B values, and after this equating, so we are going to find out the A. So this is called simple relationship between the edge length of the cube and the radius of the sphere. We got the A is equal to 2 root 2 R. So after this getting, so we are going to directly, that is a formula, that is called packing efficiency. Packing efficiency in face-centered cube is equal to how many spheres I am going to consider, because of the 4 spheres will be there, right, in packing efficiency. So here the volume of sphere and face center is how many particles will be there? 4 particles will be there. That is called into 4 I am going to multiply, because in simple cubic unit cell only one particle is there. In body centered 2 will be there. In FCC we are going to obtain the 4 particles will be present. That's the volume of sphere into 4 divided by volume of cubic unit cell into 100%. So here you know that packing efficiency. So volume of sphere you know already 4 by 3 by r cube into how many particles should be there in FCC? 4. So divided by volume of the cube. Volume of the cube is equal to length into breadth into height. That is called a cube. A cube is we got the value a. Right? A is equal to 2 root of. A cube is I am going to write directly this 2 cube. 2 cube is 8 and this root 2 cube into r cube into 100. So this r cube and this r cube will be cancelled and this 4 1 and this will be the 4 to cancel remaining. So this 3 comes to denominator, that becomes 4 by 6. So for this simple calculation I am going to write the directly the packing efficiency in the percentage. So you are need not to waste the time doing this calculation. We are going to obtain the packing efficiency called 74% of the packing efficiency will be present in the face-centered cubic unit cell or HCP or CCP. So this is called 74%. And what is the remaining vacant space which is going to be covered? So therefore vacant space which is available in face-centered cubic unit cell, that is called 100 minus 74, remaining will be 26. Only 26% space will be there in face-centered cubic unit cell.